All right, so I think we're ready. I think we're ready for chapter four. So chapter four of our workbook, it starts on page 121. Easy number to remember. It's very symmetrical. So typically in a math course where we're looking at what's called linear relations, linear linear relations, we usually start with patterns just like this, and very often you might start with one square, and you might say that this is figure number one or diagram number one. So figure one. And nothing too special here, it's just a box. Now we could also look at another figure down the line. Okay, not too interesting yet. The illustrative examples, I'll admit, I'm just going to close my window here. The illustrative examples, I'll admit, are a little bit boring to start, but they are at least instructive. So figure two has squares as well. We might begin to see a pattern here. Figure three is composed of squares as well. And because this is a bit tedious, I'll just draw one more. And hey, maybe you'll be able to notice some kind of a pattern here. And then, oh gosh, that's the worst line ever. I'm not the best artist, I'll admit that. Okay, so this is, let's call this figure four. And let's say that this pattern continues. So this pattern continues. You could conceivably draw a figure five, a figure six, a figure seven, and so on. And let's look at some relationships between the figures that are drawn and where they come up, how we've numbered the figures. So if we look at figure one, and let's draw it like this, figure one, then so for figure one, how many squares exist in figure one? Well, one. One square exists. For figure number two, how many squares exist? Well, 1, 2, 3. So 3 squares. So 1 square for figure 1, 3 squares exist for figure 2. For figure 3, how many squares exist? Well, if you count carefully, then you'll see that 5 squares exist. And then for figure 4, you can clearly see, that 7 squares exist. 7 squares, right? If you count carefully, you could say 1, 2, 3, 4, 5, 6, 7. 7 squares exist. And what we can do here is we can eventually find a pattern and leverage that pattern to find out how many squares would be in figure, let's say, 89. How many squares would be in figure 89? That would be hard to count if you were just drawing figures one after another, right? You would have to draw 85 more figures with many, many more squares, and you would probably make some sort of error in there somewhere. So we need some kind of systematic way to be able to predict the number of squares that would be in figure number 89. So what we need to do is we need to find a relationship. We need to find a relationship between the figure number and how many squares we see. One thing we can notice is that jumping from one figure to the next, if we jump from one figure to the next, and for some reason I can't switch my pen to black here, so I guess I'll be stuck in red. So if we want to go from one one figure to the next, we could say we're always going to add 2 squares, right? If we're going from figure 2 to figure 3, well, how many squares did we end up adding? We ended up adding 2 squares. And if we wanted to go from figure 3 to figure 4, well, we can see clearly that we are just adding 2 squares. So coming up with some sort of equation, here we go, I have a different color. Coming up with some sort of equation to relate these, we could say, the number of squares, I'll just call that S. So S is the number of squares. So the number of squares should be equal to the figure number. So F we'll just call the figure number. And how much are we adding every time? Well, we are adding 2 every time. So if you want to go from figure 1 to figure 2, you would add 2 squares every time to get to the next figure. If you go from figure 2 to figure 3, you add 2 squares. If you go from figure 3 to figure 4, you add 2 squares. If you want to go directly from figure 1 to figure 4, you would add 2 squares 1, 2, 3 times. So 2 is clearly our multiplier here, right? If we're doing repeated addition, this is repeated addition that we're doing. If we're doing repeated addition, typically we don't call it repeated addition, we call it multiplication. So here, if we're doing repeated multiplication, by adding 2 again and again, then 2 will be our multiplier against our figure number. And so you could say, all right, this is my equation, right? The number of squares in my figure, it's just going to be 2 times my figure number. And we could test this out. So we could say, we know that for figure 1, we're going to want 1 square. For figure 2, we're going to want 3 squares. So let's test this out. Is the number of squares, when we plug figure number 1 into this equation, is the number of squares going to be equal to what it should be, which is 1? Is that going to be equal to 1? No, it's actually not. It's going to fail. Our equation is not good yet, and we could see by trying to use this equation one more time. So for figure number 2, would this equation predict the number of squares that we should see in figure number 2? Well, for figure number 2, we should see 3 squares. And so if we plug 2 into this equation, are we going to get 3 out? No, absolutely not. 2 times 2 is 4, and 4 is not equal to 3. So what could we do in order to fix this? Well, we can see that in each of these cases, right, 2 times 1 equals 2, and 2 times 2 equals 4. We can see in each of these cases, here we wanted 1, here we wanted 3, and we can see that in each of these cases we are only 1 off, right? So to get from 2 to 1, all you have to do is subtract 1. To get from 4 to the correct answer, which is 3, all you have to do is subtract 1. So we can actually fix this equation by subtracting 1 from every result. So let's see if our new equation works. Will this little fix allow us to predict the number of squares that will be in the proper diagram or the proper figure? So let's see. For predicting the number of squares that we'll get for figure number 1, we can just multiply the figure number, which is figure number 1, by 2 and then subtract 1. That gives us 2 minus 1, which is 1. That's exactly what we want. Let's try it again. Let's try for figure number 2, if we say f is equal to 2, so we're looking at figure number 2 here. If f is equal to 2, will we get the right number of squares out for this new equation? Well, 2 times 2 is 4, minus 1 is 3. 3 is good, right? That's the number of squares that we want. So this looks like, this equation looks like it's predictive for relating the figure number and the number of squares in that figure. So for predicting the number of squares that would be in figure number 3, we just plug figure number 3 into our input here. for f. And 2 times 3 is 6, minus 1 is 5. That's good. And then finally, for figure number 4, will this predict the correct number of squares? Well, for figure number 4, we just plug 4 into f, and then we do the arithmetic. 2 times 4 is 8, minus 1 is 7, and that's good. So it looks like this equation is actually an equation that works. So this equation works for predicting how many squares will be in whatever figure number we plug in. Why is this useful? Because this question that we were given, what is the number of squares that would be in figure number 89? Well, we can now use this equation, this relation that we have created, and we can use that to predict how many squares would be in figure number 89. So if we kept on going and kept on going and kept on going, so let's say we have figure 89, how many squares would be here? Well, let's try it out. S equals 2 times the figure number minus 1. So for figure number 89, we'll just take 2 and multiply it by 89, subtract 1. What is 2 times 89? Well, 2 times 80 is 160, and 2 times 9 is 18. So 18 plus 160, that should be 178, minus 1. And here we get 177 as our final answer. How many squares would be in figure number 89? 177. And that would take a while to draw. So it's very, very useful to have an equation here. And hopefully that is a helpful illustrative example. There is another similar example in your workbooks. So if you go in your workbooks on page 121 and you look at example number 1 on page 121, they do a similar example. It's a bit more complicated. It's with perimeter. It still works with squares, but they're not interested in the number of squares. They're actually interested in the perimeter of the overall figure. It'll be another linear pattern, another linear relation. So I suggest after watching this video, try to do example number 1 without the help, without the answer, without looking at the answer, and then confirm whether you got it right or not. And if you didn't get it right, then let me know and I can help you over Microsoft Teams, or maybe even I can help you over email. And in the next video, we'll do another example which will hopefully clarify any confusion that you might have gotten from this one.